using a symbol table in a program, in a compiler. You obviously, if you look at a typical programming language, there is a certain number of possible identifiers that can be used. If you, just to simplify things, let's assume that the identifiers can't be longer than 16 characters. They have to start with a letter, and they may then be followed by a letter or a digit. So that means that you have 26 plus 26 times 36 for 2 characters, plus 26 times 36 times 36 if the identifier is of length 3, and so on and so forth, all the way to 26 times 36 to the power of 15, which would correspond to the number of identifiers of length 16. So what that means, we don't really need to know how much that is. What we do know is this is an awfully large number. Every one of these identifiers can occur, because if you say, well, I'm discriminating against this particular identifier, guess what? I'm going to use that in a program, and then your compiler fails. Obviously, every identifier that is possible will have to be accommodated. Now, at the same time, I suspect that none of you have ever written a program with more than 1,000 different identifiers. So it is quite clear that the number of identifiers that a typical symbol table has to accommodate of a program is much, 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 much smaller than the number of possible identifiers. So what that means is that we really want to have a relatively small symbol table, call it H, and we have to have a mapping from that very large set into that rather small set of n elements. So what that means is that even though every possible identifier has to be accommodated, the fact that we know that there are not that many in a typical program allows us to limit the size of the hash table to something that is significantly smaller than the number of total identifiers. So what that means is we really have to have a mapping function, H, that maps all these identifiers into that hash table, capital H. Now, the problem with that is, of course, that by and large, if I have at least n plus 1 different elements in that big set, then there is guaranteed to occur a collision. So what that means is that there are two values, two keys, that necessarily will be mapped to the same location. And that creates a collision. So, to a large extent, the question of how to deal with hashing has to deal with how to deal with collisions. So what that means is we have a key, and we associate with that key a sequence of indices. A0 for that key k, which typically is our h of k. That's what that is. And then we have to have an additional set of keys, and basically we want to have n all together, so this goes from 1 to n minus 1. And the idea here is that every key is associated with a sequence of indices. Each of these indices is a location in that hash table, and for reasons that will become clear a little later, in contrast to what I usually do, I like my arrays to start with 1. In the case of a hash table, it is more convenient to start with 0. So if we have a hash table of size n, then our hash table is numbered from 0 to n minus 1. And so that means that each of these indices, a, I, k, has to be between 0 and n minus 1. For all of them. Now, the first one, of course, of these indices is h of that key. So that's where we start. But of course, because there are collisions that necessarily will have to occur, not always, we'd like to minimize the number of collisions, but certainly we are guaranteed to encounter them if we just have enough elements, keys k, that will be used. So the remaining indices in that sequence, that's why I put a semicolon after the first one, all the others then are essentially related to resolving a collision. Now, the whole issue here is that in hashing, we can do only two things. We can do insert, and we can do search. There is nothing else we can do. In particular, we can't do delete, and I will justify that in a minute or so. But first, we have to look at what is the process that we carry out. It turns out that insertion and searching are really very, very similar. It is a situation that is very reminiscent of what we have in search trees, where, again, the insertion into a search tree and the search for an element in a search tree were very similar. The process was essentially identical, except that the termination condition and the conclusion were different. So in the case of hashing, what we're going to do is we start by using the first index in the sequence associated with the key. So let's assume we're going to insert the key k into a hash table. Now, there are three possibilities that can be occurring when we do that index. And of course, we do it first for the first index, but then we will repeat under certain conditions with the second, third, fourth, and so on index. So we do the A0 of k. So we look at H, capital H of A0k, and we have now three possibilities. The first one is that there is in that location that key k. Now, in the case of insertion, that of course is fatal, because just like in a search tree, hash tables do not allow duplicates. So if k is already there, then k cannot be inserted again. And so at this point, our insertion process fails. We have to print out a message saying that this insertion is illegal because the element exists already. So k is in that location. The second possibility is that there is something in that location, but it isn't k. Well, in that case, we have to go on. This is, of course, now a collision. We have an element that had that location assigned to it. It is stored there. And so now we have to go on to the next index in the sequence that is associated. So if we were at A0, then the next one is A1. In general, if we were at AI, then the next one would be AI plus 1. So first possibility k is there, second possibility some other dude is there, and third possibility it is empty. Now that is an important issue. In a hash table, we are always having to assume that we have a marker that tells us that there is nothing there. This is unoccupied. If your keys are all positive or non-negative integers, then -1 might be a marker that says nothing is there. In general, you just need some marker. In the worst case, you need an additional bit that tells you, yay, this is occupied, and nay, it isn't. So the third possibility, if that location, h of the index that is currently being looked at, is unoccupied, then at that point we go and insert k into that unoccupied location. So that means we've now inserted. If we were to search, then obviously the three possibilities, the first one is k is there, so we found it. If we get the second possibility, something else is there but not k, then we will have to go and proceed to the next index in our sequence. And finally, if the location that we are looking at is unoccupied, is not occupied by anything, then the conclusion is that k does not exist in that hash table. So that is the way this works. And of course, the second case, the location we're looking at is occupied but with something else, is the one that forces us to proceed in our sequence of indices, because effectively that is an indication that there is a collision. Now, at this point, it should be fairly clear that deletions cannot be handled using hashing. Why? Well, if you think about this process, how do we find that something, how do we find something? We basically go through this chain of locations that is defined by the sequence of indices a sub 0, a1, a2, and so on, until, and this is one of, we have two possible termination conditions. We find k, or we encounter an empty slot, an empty location. In the first case, we found k. In the second case, we can conclude that k is not there. Now, if we were to delete an element in such a way that, of course, we would then say, all right, we deleted you, so this is now no longer occupied. What that really means is that we are breaking that chain. And so if we had an element that is going to be deleted, that would be visited along a search for another key, which ends in, say, finding that key, K. But we're deleting an element in that chain. That means at that point, this element, that location that is visited along that chain, is going to be unoccupied, which means we would erroneously conclude that the element, the key K, is not in the hash table. We know it's there because we put it there, but because we broke that chain, we won't find it. And so that is an illustration why deletions cannot be handled appropriately in hashing. And so that is where hashing basically fails. It can only handle insertions and searches, but it cannot handle deletions, which of course can be handled using search trees, for instance, particular AVL trees. So now, one of the obvious assumptions that we want to make is that not only are these indices between 0 and n-1, given that the hash array has indices between 0 and n-1, we really now, for all k, would like to have the following property: A0k, A1k, through a n-1k, this set is exactly the set 0 through n-1. Now, there are obviously n elements in here, but it does not guarantee that none of them are repeated. Now, stipulating that these n elements are exactly those n elements means that there are no repetitions, because there are n elements and there are n elements, so there is every element here has to have an element here that is equal to it, and so that means that there are no repetitions, and that, of course, is what we want to stipulate, because if we do that, then we are guaranteed, if we go through that entire list, this entire sequence of indices, we are guaranteed that we will visit every element in the hash table. And that, of course, is the key to knowing that we are going to be able to find everything with a minimum of space requirement. Now, we will have to come back to that because there are other issues, but we certainly want to make sure that every location in the hash table is fair game. And in order to achieve that, we want to make sure that this condition is satisfied. If, just to give you an example, this were for all keys 1 through n-1, then it follows immediately that neither H0 nor H1 nor H2 would ever be used. Clearly, we do not want that, so we are stipulating that that is, in fact, equal to 0 through n minus 1, meaning that every location in the hash table is, in fact, usable, and that is the one of the fundamental requirements for hashing. Now, we still have to look at how do we deal with those collisions, because ultimately what we have is that we want to make sure that the way in which we are using the sequence in both insertion and searching is, in fact, fairly efficient. So, obviously, there is no way that one can store that sequence for every k. We don't even have enough space to store every k, never mind a sequence of length n associated with every k. So what we need then is we have this function h, which maps each element in the set to a location in the hash table. And then we basically have to have an algorithm, a formula, that allows us to determine those additional values, the A1, A2 through AN minus 1. And so what we need then is a way of creating these. Now, ideally, what we would like, and I'll come back to that in a minute, ideally what we would like is that these sequences all be completely random. If there were, then there would be very nice properties. And so what we really want to do is we want to the extent possible, get as close to that as we can, that these sequences are random. And we will talk a little bit more about how this manifests itself. So the first way would be linear probing. Linear probing basically says that we take AI of k and we define it to be AI minus 1 and k plus 1 modulo n. This is, of course, where it is convenient to assume that your array starts at 0, because that way you can take things modulo n. This, of course, guarantees that this is going to be between 0 and n minus 1. And so that's where that becomes convenient to assume. So even I have to agree that the array goes from 0 to n minus 1 rather than from 1 to n, which I usually do, because it is much easier to write it down. So in this particular case, what we basically do is we find, so if this is our array, H hash table, we find our H of k, which of course is the A sub 0 k. And now we're going to look at, is it k? Depending on whether we're inserting or searching, we can stop at that point, either by saying that the insertion is illegal, or we, in case of search, we can say we found it. or it is occupied by something else, in which case we have to go on to the next index, or it is unoccupied, in which case, in the case of insertion, we are going to put it there. And in the case of search, we're concluding that K does not exist in the hash table. So, assuming it is occupied by something else, we now go to the next position. Now, this is +1. So this is the very next location. And so this is A1. And then if that's the case again, we go to A2 and then A3 and so on. And so you can easily see that when we start here, we're going to go through that, if all of them are occupied, until we hit, say in the case of insertion, until we hit here an unoccupied location, and then we'll put it in there. So basically, we've now inserted this element, and that means we are going from one position to the very next, to the very next, to the very next, until we actually find an unoccupied position. Now let's assume that we have another key, K1. So obviously we're going to put that there. And let's say it is here. So that is inside of the block that we had to traverse for K. Now, as you can easily see, K1 starts somewhere else. So the A0 of K is different from the A0 of K1. But once they meet at this point, the chain is going to be the same, because we're just going to go to the next value and to the next value and to the next value until, well, we find this one where we put K, and then the next one is unoccupied. So now we're putting K1 there. What that means is we're now experiencing a negative phenomenon that is known as primary clustering. Primary clustering basically says that the probability of ending up in a large block is proportional to the size of the block. And because we're always enlarging a block at the very end, because it is always +1, it follows that if we hit a big block, we are going to enlarge that big block even further. Because if we start with A0 in a big block, we are going to add an element at the end of that big block. And so what that means is that the rich become richer. And in addition to that, you have the following additional problem. If you have two large blocks, eventually this one will grow, and then more and more, and eventually those will merge. So the likelihood that two large blocks will merge is probably greater than two small blocks will merge. And that, of course, has major implications, because the complexity, the number of probes that has to be carried out, is proportional to the size of the block in which you end up in linear probing. So in this case, what you are ending up with is a situation that makes things quite unattractive, because big blocks will coalesce with other big blocks to form even bigger blocks. And since a big block requires more probes than a small block, so if you had here a little block and you started here, well, then you would very quickly get to the point where you find an empty spot, and so for insertion you would insert that quickly. So you really don't like large blocks, and you certainly don't like the fact that large blocks in linear probing will more likely coalesce into even larger blocks than small blocks. And so that is an undesirable situation. So what you want is to see how you can avoid primary clustering. Now, primary clustering can be avoided by changing the definition to reflect that we want to have a time dependence. So instead of incrementing by 1, we're incrementing by I. This is called quadratic probing. The difference here is that this was always 1, this is now I, which means that if you have an overlap, now of course if both of them start at the same place, if you have this sequence for K, and you have another sequence for K prime that starts also in the same position, then that is not going to give you an advantage. But if you are if you have the following situation, you have your K starts here in this place, and then the next position might be where K1 starts. Well, so that means they have an element in common. But then the two chains will diverge, because K1 will have 1, and then 2, and then 3, and then 4, whereas K has already used up that I is equal to 1, and then it will go 2, so they don't coincide here, and then we'll go 3, so they don't coincide here, and then we'll go 4, so they don't coincide in here, which means that even though they happen to have a location in common in that chain, in these two chains, they diverge because in quadratic probing, the number of the probe I here is not probe I there. And so that means that the two chains diverge, and that means that even though you may have one element in common between the two chains, that doesn't mean the two chains stay the same, as they did in linear probing, because once they have an element in common, adding one in both cases is going to give you exactly the same thing. In quadratic probing, you may add 2 if this was the second, and you may add 3 if this was the third probe, and therefore they will diverge even though they have an element in common. So this is the advantage of quadratic probing. It does, however, have a little bit of a problem with this requirement. In general, we can't really guarantee that we're going to visit all of the elements in the hash table. And so, for that reason, quadratic probing, even though it has some advantages, is not really that attractive. What we are using is double hashing. So what is double hashing? Well, we started out by saying we have a hash function, h of k, and now we are stipulating that there be another hash function, hh, which has to be independent of h. So it can't be the same, it has to be very, very different, has to behave differently. You may say the first hash function, if you have strings of a certain length, the first hash function h may be based on all odd positions in the string, and the second hash function may be based on all even positions of the string. Clearly, if these strings are uniformly distributed, the two hash functions are completely independent, and so they would satisfy that requirement. And then what that means is we're going to take our key k, and we obtain a value z by applying hh, the second independent of h hash function, to the key. And then ai sub k is defined to be ai minus 1k plus z modulo n. So that reflects the idea that we do expect, even if for k1 and k2, h of k1 is equal to h of k2, meaning that we have a collision, we probably, given that we're assuming that hh is independent of h, we probably will get that hh of these two keys is different. Which means, of course, that the chains are going to be different. Even though they start at the same point, they move differently because they go by z, and if this is different from that, then these are different z values, and so the step size is different. Now, this is, of course, somewhat fraught with danger, because let's look at an example. Suppose I have 0, 1, 2, 3, 4, 5, and let's assume that this is occupied, this is occupied, and this is occupied. So half of the table is empty. Now, if I'm not careful, if h of k, which is the one I want to insert, is 0, and h of k is 2, I am going to be screwed. Because I start here, this is occupied, so I go to plus 2, this is occupied. I go plus 2, this is occupied. I go plus 2, I'm here, and then I just loop around here, and I will never figure out that actually half of the hash table is free. Now this, of course, has to do with the fact that the size of the hash table in and the z that I'm dealing with are not relatively prime. In this case, they're 2, 6, and 2. GCD is 2. And that, of course, is why this breaks down. So what we have to do then is we have to make sure that this z is actually useful. So what does useful mean? Well, it has to obviously satisfy this GCD requirement. GCD of n and z has to be exactly 1. This is first stipulation. And then, of course, we also have to stipulate that z can't be 0, because if it is 0, then nothing changes. We're stuck at that one location, and clearly we don't want that. Okay, so how do we get this? Well, this is, of course, where in contrast to virtually everything else in computer science, when you store information in a large array, you probably want to have something that is a power of 2. That is the one situation where that is very bad. What you really want is that n be a prime number. Very rare that you want that to be a prime number when it comes to storage. We've talked about RSA and encryption and so on, yes, but these are the numbers. Now we're talking about the number of values that we have in an array, and typically we're going to go with round numbers, most of the time powers of 2, but in this particular case, in the case of a hash function, we actually want that size of the hash table to be a prime number, because if this is a prime number, if n is a prime number, then GCD of n and z is always 1 as long as z is not 0. So if z is 0, in that case, we just change it to some other value. For instance, z is equal to 1, which will work with that. And then we can completely carry out what it is that we want to do for either insertion or searching. And that then means that we have a situation where this clustering business is not as big a problem as it was in linear probing. Now, double hashing is an approximation of random. As I said, this sequence A0 through AN minus 1 ideally should be completely random. We can't really do that because it would just computationally be exorbitantly expensive. But it turns out that double hashing is actually a reasonably good approximation for that. So, what does that buy us? Well, we need one more concept. We need the load factor. What is the load factor? Typically denoted by alpha, and that is the number of occupied locations divided by the number of locations, which of course is n. And now the crucial issue here is we are going to stipulate that alpha has to be less than or equal to 0.8. Now, that is a very serious issue, because essentially what it says is you have to guarantee that you are going to waste a quarter of your space. If your load factor is 80%, that means you can only use 80% of your hash table. Less than that, actually, I would hope, because at one point you may want to insert, and if you exceed the 0.8, then you're in big trouble. So that means that of the available space, useful space, you over and above that, 1/4 of that at least has to be wasted. 20% is what is not useful, and so 20% is 1/4 of 80%, which means you basically have to be prepared to waste at more than 1/4 of the space. If that creates heartburn for you, then hashing is not for you. However, if you can handle that, and of course there's an additional issue, which has to do with the fact that all you can do is insert and search. If that is the case, then for searching you need typically approximately 2 probes, independent of the size of the hash table. So that is an extraordinarily efficient result, because it basically says, independent of how many elements you have in your hash table, 1,000, 1,000,000, 1,000,000,000, it still takes only 2 probes. Now, of course, if you have 1,000,000,000, if your n is 1,000,000,000, then 1/4 of the useful space, which is 80% of that, is going to be wasted. You're going to be wasting 200 million of the 1 billion that you are allocating. But the advantage of that is that you're going to get access to elements searching in approximately a little bit more than 2 probes on average. Now, this is the other issue. This is an average argument. If you have a hard real-time application, fly-by-wire airplane or nuclear power plant, that isn't going to work for you, because things can go wrong. How can they go wrong? Well, if you know how everything is set up, it is quite possible that you're going to have all these elements clustered together. If I know everything about your setup, I know all your two hash functions, then I can always cook up a sequence of keys that guarantees that I have everything clustered together. So this is obviously, load factor here is less than 80%. But if I start here, then I will have to go through, I can assure that I will have to go through this one by one. And as a result, I am going to end up with a time complexity in the worst case that is order of n. So this is only for average, and it is only possible if you keep your load factor low, less than 80%. And that, of course, implies that you have to have a very good idea of how many elements you actually will have to accommodate. If you don't have a good idea, then hashing is probably not for you, because if you exceed the load factor, then what that really means is by the time you get to, say, 85%, you then have to stop inserting. You have to come up with a larger new hash table. You have to insert all the elements that are currently in the old hash table into the new larger hash table, and only then can you continue inserting. So this is, of course, a highly undesirable situation, which you really don't want to run into, because ultimately you're not satisfying the assumption that you have a good idea of how many elements you're going to have to accommodate. Having all said that, nevertheless, we are looking at here a fabulously attractive method if all of these conditions are satisfied, because you basically have to do almost nothing. 2 probes. So you may say, well, that doesn't sound right. How can that be? Linear binary search requires log n. That depends on n. Well, let me point out to you that if you had an index for the element, you'd need 1 probe. That's all. You'd go there. And if you, at a different level, remember the average argument that I made for finding an element in a linear search where the probability distribution is quite lopsided. Probability of being in the first position is 1/2, being in the second position, 1/4, being in the third position, 1/8, and so on. Well, in that case, you again needed 2 probes. So this is not as crazy as it looks. And in fact, hashing is an eminently practical situation if all the conditions that I've enumerated are satisfied. Any questions about hashing?
I don't have a question about hashing, but I have a question about submitting the assignment.
Yes.
For submitting the assignment, I tried submitting it to the website, the 3320 at cs.uh.edu.
Yes.
I tried submitting a few times, but I kept getting confirmation from Box saying that it wasn't sent successfully.
What did it say?
It said the file wasn't sent successfully to. It said your attempt to email the following files into 3320 was not successful.
Did anybody else submit? When did you do that?
I did today.
You'd simply emailed it to 3320 at cs.uh.edu.
Oh, yes.
I did not set this up. The IT people in the department set this up. I can't answer that. Try again and see whether you missed something, but if there's any question, if there are problems, I will find out, and if I have an answer, then I will send it out. And this is the first time I hear about that.
Okay, thank you.
Sorry about that. Any other questions? All right. In that case, we're going to go to a new topic, and that is graph algorithms. So we first start with graphs, and a graph basically is a pair consisting of vertices or nodes and edges. And there are two different types of graphs, the directed and undirected graph. Undirected, directed. In the case of an undirected graph, an edge is basically a set consisting of two nodes. They're also called vertices. In a directed graph, you have pairs, U, V, and of course, you may want to view an undirected graph in terms of a road map where all the roads are two-way streets. If you can go from U to V, you can go from V to U. A directed graph could be viewed as a road map in which roads are one-way streets. Now, of course, it's fairly obvious that if you can go from U to V and from V to U, you can model that in a directed graph by having two edges, one from U to V and one from V to U. And so that then shows you fairly clearly that any undirected graph can be represented by a directed graph in which you simply make two directed edges for each undirected edge. But obviously, the converse isn't true. You may have something like this. 1 goes to 2, goes to 3, 3 goes to 2. Well, in this case, you can go from 1 to 2 and from 1 to 3, but you cannot go from 2 to 1 or from 3 to 1. Whereas if it were undirected, you might have something like this. And so in this case, you have clearly a notion of connectedness that is not quite that obviously reflected in the directed graph. Clearly, 1, 2, 3, this graph is connected however you want to define it, but this graph, the directed graph, isn't really that obviously connected. In fact, you might argue that because you can't go from 2 to 1 or from 3 to 1, it isn't really connected in the way this graph is. We have two different ways of representing graphs. And so from now on, we'll just look at directed graphs, because clearly whatever we can do with an undirected graph, we can do with a directed graph, but not conversely. So directed graphs in that sense are more general. And so we have two ways of representing things. We have using adjacency lists, and we have using incidence matrix. An adjacency list is basically an array where you have it's an array of pointers, one pointer for each node. And the list that is associated with that node is the list of all the directly connected nodes, edges. And an incidence matrix, you basically have a Boolean matrix where you have false if there is no node from I to j, and you have true if there is a node from I to j. Now we'll assume we have m edges and n nodes. And so for all practical purposes, because we don't really permit u equal to v, even for the directed graphs, because, well, that would sort of give you a situation like that, which is, well, if you deal with automata theory, you probably have these, but typically you don't have these kinds of things, so we disallow them. So we have u different from v, and that means that m is certainly no more than n times n minus 1, which is order of n squared. M, of course, could be 0. If we don't have any edges, then that's still a graph. It probably is not a particularly useful graph, but that's neither here nor there. No judgment is being passed here. But certainly m could be as large as n order of n squared. So let's look at an example of a graph, which I'm going to use several times. We have 1 goes to 2 and 3, and 2 goes to 4, and 3 goes to 5, and 4 goes to 6 and 7, and 5 goes to 4, and 6 goes to 5, and 7 goes to 3, and 8 goes to 7. So what we have here is a graph. It's obviously a directed graph. And if we were to represent this in terms of the adjacency lists, we'll have 1, 2, 3, 4, 5, 6, 7, 8. And 1 would go to 2 and 3. And 2 would go to 4. And 3 would go to 5. And 4 would go to 6 and 7. And 5 would go to 4. And 6 would go to 5. And 7 would go to 3. And 8 would go to 7. So these are the adjacency lists. And the incidence matrix would be, well, we have a 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And I assume that if I don't write down anything, it is false. So we have 2 and 3. 2 is 4. 3 is 5. 4 is 6 and 7. 5 is 4. 6 is 5. 7 is 3. And 8 is 7. So this would be the incidence matrix. Now, if we look at the space that is required to represent a directed graph with m edges and n nodes, it should be fairly obvious that I need n squared space to represent it using the incidence matrix, because I need one entry for every combination I and j, and there are n squared of those, and so that is independent of m. In the case of the adjacency lists, well, I obviously have to have n, because I have n lists that are indicated by that array of pointers. And then for each of the edges that I have one entry. So this is n plus m. So obviously, if m is the maximum, then this is again exactly n squared. But of course, this could be much smaller. If you have a grid, 2D grid, where each node has at most 4 neighbors, so this node has 1, 2, 3, 4 neighbors. Each node has at most 4 neighbors. In that case, m would be actually less than 4n, so this would then be order of n rather than n squared. So the representation using the incidence matrix can be significantly more costly than the representation using the adjacency lists. However, there are certain things where one has an advantage over the other. In particular, if I have an incidence matrix, it will be very efficient to find out whether a particular edge exists. So if I want to know whether there's an edge from 4 to 1, all I have to do is look at the entrance for 1. And this is false, and therefore there's no edge. If I want to look at 4 and 1 in the adjacency lists, well, there's 6, that's not 1. There's 7, that's not 1. And then I get to the end of that list, so I can now conclude that 1 is not in that list. Since, in general, those lists can be of length order of n, because in the worst case, there are n minus 1 elements, I may have to go through the entire list in order to determine whether or not an element exists. So in this particular case, it follows, therefore, that by and large, determining whether there exists an edge between two given nodes, is a more costly process in the case of the adjacency lists than in the case of the incidence matrix. In the case of the adjacency lists, in the case of the incidence matrix is order of 1. The case of the adjacency lists, in the worst case, it is order of n, which of course is significantly worse than order of 1. However, at the same time, you are looking at a much more economical representation using adjacency lists rather than using the incidence matrix. And so one thing that we're going to look at next time on Monday is what is the computational complexity, time complexity, to convert one representation to the other one. So to go from an adjacency list to an incidence matrix, or to go from an incidence matrix to an adjacency list, and then see what that requires in time, because if this were to be very efficient, then obviously we may want to do something accordingly. However, as we will see, it isn't that efficient. Anyway, that's the end of what I wanted to cover today. Any questions?
Yes. If I'm having trouble sending it to the first email, can I send it to like your instructor email?
No. If you have problems, then everybody else will have problems too. I don't. Yeah, no. If it doesn't work, then we'll have to see what we can do. In which case, I'll just send. If you can't submit it, then I'll send out an email eventually once I know what the problem is.
Okay, thank you.
Okay. Any other questions?
So are the TAs gonna email our grades by today, or?
That is the idea.
Okay. Through email, right? Not through Blackboard?
Pardon?
Through email, correct? Not through Blackboard?
I would imagine through email.
Okay. Thank you.
Okay. Any other questions? All right, then I will talk to you on Monday again. Bye-bye.